Hi guys, so here we have it, lesson 2 of the particles module, states of matter. If you remember from the introduction, this is pages 39 and 40. I'm going to take 2 lessons to do this one, because there's quite a lot to take on, particularly in lesson 3. So if you need a textbook to keep up, page 39. So one of the early lessons you learn is that all particles arrange themselves in one of 3 states of matter. At that point, usually some kid puts his hand up and says, what about the 4th? And then if you're really lucky, another kid will put their hand up and say about the 5th. So the 4th is plasma, and the 5th is Bose-Einstein condensates, neither of which you need to know about until maybe degree level. So for now, we're going to keep it really simple. And when you're in year 7, we usually do it from the point of view of little snowmen. So that's where I thought we'd start. Seems weird talking about snow given the weather, but let's take it. So, states of matter. We all live surrounded by water. It's one of the special things about our planet, and it's special because it can exist in one of 3 states of matter. So let's take the first state, and that's solid. And you all know, I'm not telling you anything new, that in solids the particles are arranged very closely. Feel free to make notes at this point, even draw a snowman. But the particles are moving. They're vibrating, but by a very little amount. And a state of matter is completely dictated by the average energy each of those particles have. So even ice, the particles are vibrating. And in fact, there was an experiment done a long time ago by a guy called Lord Kelvin. It was great. In the old days, you didn't have to be royalty. You could just be a lord. And he did a practical. And he looked at volumes of gases and the temperatures of those gases. And if you've ever left a balloon out at night and then come out, seen it in the morning, it's a sorry sight because it shrinks. But if you warm that balloon up gently, it'll grow again. So he decided to do a little practical. There's 0 degrees Celsius. And he measured the volume and he heated up a gas and it came out like that. And when you drew a line of best fit through the coldest temperatures, way below he could achieve, he always got to minus 273.18. So he tried it with a different gas and drew his line of best fit. And again, always converged upon this number, minus 273.18. And what he'd actually done is discovered absolute zero. Absolute zero. And the reason I'm telling you this is that absolute zero represents a theoretical number of no kinetic energy for those particles. So if you're at minus 200 degrees, for example, you've got loads of kinetic energy still. And this number, minus 273.18, is impossible to achieve. The closer we get to it, the more quantum mechanics takes over and adds that little bit of quantum kinetic energy. But that's a tale for a different day. So, back to our story. In solids. Now, solids are solids because the bonds between the particles, you can imagine them like little springs. The bonds are very strong. And that holds the solid together. It's the reason you're a solid, not a liquid. Like so, and it's holding every particle together very strongly. So they're vibrating, so it's small vibrations, strong bonds, and that means they are close together. And because they're close together, based on last lesson, they're usually dense. In terms of, take a square cube and you'll get more particles in it on average than, say, compared to a gas. So that's a solid. But solids don't last forever, particularly snowmen. So I hate this one, but it's the best I could find. Let's take this one. Oh dear. It's so sad when you were a kid and you build a snowman and you come out the next day. I'm sure it can traumatise you. So they can turn into a liquid. So what's going on with a liquid? Well, we're going to have to add in heat energy. It's the most obvious thing in the world when you're a young kid and you learn that heating things up turns ice into a liquid. So let's have a look. We'll have a container. This time the particles are still bonded, but they have weaker bonds. And that means there's mobility. Those particles now can increase their distance. They become more mobile. However, the bonds are still there, and hence liquids stay in the bottom of the container. So they're vibrating faster. So I'll add some vibrational movement to that. So we can say still quite dense, but weaker bonds. And this is why you can run your hand through water and pull water away from the other ones. You try it with ice and it's a different task altogether. So weaker bonds, more vibrations. And the final one is obviously gases. Every time you've ever boiled a kettle, you'll have seen the steam coming out of the end. So the liquid water has changed state and it's become a gas. We call that steam, but technically it's a gas. So a gas. Let's try that again. I'm going to get rid of that. Melting snowman is traumatizing me. So if we take a gas, gases are, like, I always think of them as ADHD kids giving Kiora Orange and Skittles. Imagine you've got the room and you was looking down. Gases are crazy. They just go and go and go. They have so much kinetic energy. They've broken free of everything else, all the other bonds. The perfect gas would have no bonds. So you may hear this word, a perfect gas. And what it's saying is there's no bonds, no red on this at all. And they're hitting the sides like so. And we do more about gases on lesson 4, so I'm not going to go into it too much. Other than, as you can see here, they are less dense. And one of the features is then, it means they are compressible. I'm going to spell this wrong. Compressible. I have definitely spelled that wrong. Oh, well, you know what I mean. They're less dense, so they've got loads of empty space in between them. So you can compress a gas. It's why they're really good for putting gases in tyres. Is that Sybil? That's bugging me now. I'm sure you're all shouting at the screen. So, less dense, they're compressible. They have lots of vibrations. They fill the container. And I think that's it. I don't want to go too much into gases because that's going to be a separate lesson. So that's the notes for the 3 states of matter. And the other thing is, what are the names of the changes of states of matter? So you may see it written out like this. So we take a solid and then we go over to a liquid. And then over to a gas. And you just need to be familiar, and this will be really easy. Familiarity with the names of the processes as they change from one to another. So if I go from here to here, oh, wow, that was big. Try that one. And I'm going to go red for heating up. So if we add heat energy, we go this way, and we go this way. And we end up with going from a solid to a liquid is going to be called melting. So you'll hear them talk about melting points of solids. So e.g. melting point of H2O is 0 degrees Celsius. And when you are doing your A-levels, hopefully some of you'll do physics or chemistry, you'll do it in terms of Kelvin. And if you think back to that graph I did, you see that 0 degrees Celsius is definitely not 0 really. minus 273.18 is. And so Lord Kelvin got his name in there, and he called that 0 degrees Kelvin. So actually, 0 degrees Celsius is positive 273.18 Kelvin. And so in physics, you would put the melting point as 273 Kelvin. Now, it used to be in the curriculum. They stopped it with this new one that I'm teaching you. But I think you need to be shown that this is coming your way. So all scientists use Kelvin. We don't use degrees Celsius. So that's melting point. Once we go from a liquid to a gas, there we're talking boiling. So can you guess, before I say it, boiling point, boiling point of H2O, how many Kelvin would that be before I write it? Well, if it's 100 degrees Celsius, then it's 373.18 Kelvin. We're just literally adding on 100 to the last number. And that's the handy thing. 1 degree Celsius is equal to 1 Kelvin. So luckily they didn't come up with any other strange ways of doing it. Right, what about the opposite ways? So we've got the losing heat. So here we are losing. I nearly put loosing. Here we are adding. Just label those up. Add heat. Here we're losing. So going this way, we're going from a gas to a liquid. Here we're condensing. And if we go from a liquid to a solid, you learnt this when you was a kid, when you made your own lollipops. You've gone from a liquid to a solid. That is freezing. So those are the changes of state. There is one where you can go from a solid straight to a gas. There's a couple of materials I know off the top of my head. CO2 does that, and iodine does that as well. Iodine does not have a liquid state. It goes straight from a solid straight to a gas. And we call that sublimation. Don't think you'll get asked about that. You may in chemistry, but not with me. So I put it in there. And there is another one going straight from a gas to a solid, but I can't remember what it is. Don't think you need to know. So that ends lesson 2. I'm lining you up ready for lesson 3 because that's where it gets tricky. So master this, do the questions, have a quick go. It's really easy because lesson 3, you're really going to need to know this. Ready for it.